Hello, everybody. My name is Kevin Kocak. I'm the founder CEO of Chemical Q Device, here for event seminar 128. This is Thursday, March 28th, 2024, for large language model explainability or controllability improvements with tensor networks. So this is a specific study here that's shown on the first page. So it's basically taking apart, you can look at specific layers and tensorize them with tensor networks. So this is an MPS or matrix product state or tensor train. And a lot of times you're trying to achieve multiple different things. So if you're trying to get explainability and controllability, which is what I'm going to be going over today, you are also still trying to get expressivity. And that's what's going on in this specific one. So you'll see this knowledge distillation is more a traditional approach. It's not as, quantum inspired, but a lot of times multiple things are at play is the point with a lot of these studies. So what they were able to get was performance pretty good, compression about 3 to 4.5 times, using Intel CPU to about 2 to 3 times speed up, and then for the Raspberry Pi about 2 to 4. And what you're seeing in a lot of these is this transition into, say, like smaller mobile devices to get the number of parameters down. So what I'm going to go over here is this first part is with LLMs, just what are LLMs, what are generative AI, just very basic stuff, and how that relates to medical as well. And then the second one is traditional explainability of LLMs with using tensor network approaches. So explainable AI for LLMs is a big field on its own. You don't typically see tensor networks or quantum inspired, at least in that specific, it's like a review. So I'll go over that. And then I'll go over a bunch of more other papers that are working on this. So again, it's trying to fulfill this objective. So say if you're a doctor in an office, and then you get an answer from the AI model in this, some cloud compute, and it tells you a certain thing, and you want to look into it more. With tensor networks, they tend to be linear and a lot more explainable, as opposed to neural networks, like fully connected neural networks. So what's shown here is basically for generative AI, it's a subset of deep learning. So we have AI is the big bubble. You have machine learning, then deep learning, and then this bubble here is represented by generative AI. So this is typically like a chat GPT. You're either inputting images or text, and it's returning something based on what's generated. It's unsupervised learning. It's somewhat more of a, it's not a well, I'll get to a different slide to explain that. But with LLMs, large language models can be generative. So that's what's represented by this circle here. So it can be a part of generative AI. So generative AI models are typically large. And large can mean either the data set size or the number of parameters. I think most often I'd hear it with number of parameters, but people use large language models, to describe that. Now, LLMs can also be just part of deep learning, so meaning that they're not generative AI, they're more supervised, and this would be something like, a bigger classification model or object detection, something that's not generative in those regards. Now, how this all plays out is basically, if you're not into LLMs and you're not into generative AI, it's looking like everybody should be. The downside is, yes, they're larger, they're going to take more space, but everything's just trending up in compute size. I mean, with RAM, CPU, GPU. So essentially, to get to a foundation model, you can use text, image, speech, structured data, 3D signals, and then your foundation model is the core essence of what you can go on and do different things with text, like question answering, with images, image captioning, object recognition, these types of things. But they made a very strong point, this is Google Cloud, of getting to this foundation model, and now it can be used for a variety of different techniques. So how this plays out in medical is you have healthcare data. You're going to have millions or even more than that electronic health records. Now you have this medical foundation model, and then you see the different things. So it's not just text, it's also image analysis, risk stratification. So I think this is what you're going to see a lot, and especially, this human AI collaboration of natural language interactions. So this is still us prompting, AI, generative AI to do a specific task. But as opposed to all of these kind of smaller fragmented models that we see now, and from asking around, yes, you could still use those smaller models and they take a lot less storage, those types of things. But just on the universal, as far as like you're training on all of this data, getting to a foundation model, and then doing some other fine tunings from that. But this is your core model to output both text or images or video, those types of things. Are there any questions at this point? So that was an overview of LLMs and generative AI. And then, so these next couple slides, so this is more of the traditional approach with explainable AI. And what's shown here is basically, you have your LLM or you have your explainable AI. Now, LLMs can help explainable AI, but more commonly, or at least in this study, explainable AI can help large language models. So that's what's shown here. So they say of these, there's 7 strategies of enhancing LLMs with XAI, and 3, the other way of enhancing explainable XAI with LLMs, right? So again, they kind of fit together because if you have better explainable AI that was helped by LLMs, but this is kind of what you would see in the traditional world of explainable AI with LLMs. And the terms interpretability, explainability go hand in hand. So you'll see all these on the left as far as like the different approaches with it, attribution methods, LLM components. Now, additional study is needed with this, but some of the, the core machine learning or core technologies say are very explainable, but they're not state of the art. And I think that's where Tensor Networks is coming in, is in a lot of these studies, they can get state of the art results, meaning that they're similar to say just using neural networks, but you're also getting explainability. So it's a very, very important field. And Sam Altman of OpenAI, he's come on and talked about this, and I'll allude to that later. Basically, there's a good quote of some of the workarounds if you can't use explainable AI to a high degree if it's all nonlinear like neural networks. So here's another example here too, a review of interpretation methods. And ChatGPT, I think others too, the core essence is transformers. So if you're familiar with convolutional neural networks, well, now you're using transformers, and then you can either do it with a feed-forward network, and then this is something unique for transformers, is this multi-head self-attention. So everything on the left, for explainable going to usable, and you see different genomics and these types of things. And again, the goal is to make this more interpretable after getting the answers and like, PhD researchers or doctors understand this. And then you see this with the multi-head self-attention. So just in a nutshell, convolutional neural networks kind of slide a window pane again across an image, and then you're kind of doing different compressions along that way. But a multi-head self-attention actually takes an attention, like if it's a bird sitting on a couch or something, it can look at the bird and then see the background in the couch, and then it's using attention. So that's the main thing, is that self-attention. And then, the end goal in these is not only an explanation, but usable. And that was actually the name of the paper too, is usable, explainable AI. So this next part here is all tensor networks. So tensor networks for interpretable and efficient quantum-inspired machine learning. So a lot of these things, if they say deep learning, machine learning, LLMs, generative AI, typically you're dealing with some aspects of, transformers, those types of things. But MPS, the matrix product state, is the ideal tensor network to be in right now. It's only one-dimensional, so that can be tricky sometimes trying to get it into that format, but has the best algorithms. And, you'll see the most research as far as like the state of the art research at this point is using matrix product state. And others also exist too. You have, tree tensor networks, PEPs, Mera, and that's all being worked on as well because they have advantages. But right now, if you can get, into, so you basically have, some high dimensions that you're getting into, and you have controlled approximations to get into MPS. And then that's typically where a lot of the good solutions are right now, or with MPS or matrix product state. So basically, they say another serious issue caused by non-interpretability is robustness. And they say, for instance, a well-trained deep neural network model may be severely disturbed by noise or intentional attacks. So it's just one of those things, like there's other things that stem from explainability and interpretability. And I'll get to the kind of like the open AI kind of the solution, the patch right now for today's neural networks, as opposed to like trying to deal with it with, on the fundamental basis with tensor networks. And they brought up this case, so they call this the tensor network machine learning butterfly. So everything on the left has been shown to help with interpretability. Everything on the right is proven to be more efficient. And again, these are all based on studies, and they keep building and growing. And we'll get to the multiverse, which is kind of leading the industry in some regards of this a little bit later. And basically, they're able to keep the majority of the performance while also making it a much more controllable and explainable at that same time. So, as I said, there's just traditional probabilistic machine learning models such as Bayesian networks and Boltzmann machines, and they're regarded to be white boxes, meaning that they're transparent and explainable. However, their performance is not typically as good as the tensor networks, is what they said. And that's why, to use tensor networks. And tensor networks is just, they're so flexible, and you can represent not only just quantum circuits with tensor networks, but other complex systems. And at that same time, you can do high dimensional, low rank approximations, which is a controlled approximation, getting it into a more CPU or GPU efficient network, that tensor network, as opposed to the original data, how it was represented there. And again, so I think all of this is going to start going into neural nets. And again, it'll probably take longer on the performance end to match neural networks with deep learning, just because of all those correlations. They're nonlinear systems. But there's oftentimes, and I'll show you with the research that I did too, is that I was getting like 2 orders of magnitude better loss performance at a similar time at a fraction of a size, like 60 times lower model size. And that'll be the key moving forward. It's not just explainability; it'll be also having acceptable accuracy, loss, those things that are associated with better. Those are the key metrics, right? But for tensor networks, it's bringing in these other factors that are even more important for doctors to be able to understand more how the computer got to that solution. And then, so this is important too. So this is efficiency and interpretability. So you saw the previous graphic that it kind of breaks into two. Now, a lot of times in studies, you'll see if you're using matrix product operators, matrix product states, is that, a lot of times you're getting both. Like it's not using as much RAM, and the model size is a lot smaller. And the only thing that I see on the papers is usually they're just running at about the same speed. So I haven't seen great speed ups with it, but I've seen, especially with model compression and especially with loss performance or lower loss. So they list these as far as Born rule, quantum states represented by tensor networks. And there are things to keep in mind when developing future code, is that if it's more important that it's interpretable, you're going to have some leeway as far as like, yes, I can't get to 100% of what it was, or sometimes you can get better. But that's the goal, right? And the more that tensor networks, this insertion into today's LLMs and generative AI that can keep these existing benefits while being more explainable, the more enticing it is, they're going to be. Now, the issue that I've seen and I've heard from people is that people just don't understand quantum inspired. They don't know how to, program with tensor networks, that type of stuff. But I think those days are changing, and it doesn't take that long to get up to date. And so this is a very interesting study. This is back in 2021. Now, this is both matrix product state tensor networks, but on the left is a quantum inspired DMRG algorithm. And then you're familiar with the right one, which is stochastic gradient descent. And then what you want to see is dark reds and dark blues. And then that means that it's more interpretable. So the one on the left is that kind of darker red and darker blue, and on the right with the matrix product state, but with the regular stochastic gradient descent, you see it's just very, it just hovers around the white with a little bit of blue and a little bit of red. So I thought it was an interesting paper, and it goes back to August 2021, so it's definitely worth taking a look at. Now, there were some caveats to it, is that SGD is faster, and DMRG achieved these results decently at low epochs, but to get to the much higher performance, it would take many more epochs, okay? So there's some trade-offs, and that's where, it's kind of pulling all these papers together and see what works the best. But they say MPS can drastically improve their performance by increasing the ability to represent the feature space with a single linear. Here we go. If the takeaway, besides everything else I said, it's this linear transformation as opposed to nonlinear, fully connected neural networks, those types of things that are definitely less explainable. And if you see it in literature where it just says, okay, it's inherently known that this will be more interpretable, but they haven't gone through all of the SHAP studies or Lyme studies to get there, that it's these types of papers that are worth taking a look at, because it really explains things. Now, this next one they called multi-way multimodal transformer by multimodal learning is able to provide a multi-way attention space that consists of many-to-many interactive paths. So on the left is with the tensor contraction, and then on the right is the regular one. And they said that on the left, it can achieve the state-of-the-art comparable performance, but it's obviously likely going to be a lot more explainable, because with the tensor networks, being nonlinear by nature, that it's just a field ready to blossom. It's just, there's all these papers, and I'll get to some more papers that are basically able to prove that even more. So here's another important one. So explainable natural language processing, that this is associated with generative AI, or like ChatGPT. So NLP is what we call it. And they say, despite empirical successes of recurrent neural networks in NLP, theoretical understanding is limited due to intrinsically complex, and here's this key point, nonlinear computations. So that's kind of like a main factor that's moving against explainability in today's models, and add in, however many trillion parameters or billion parameters, it's likely not going to address that issue of being able to explain the results, okay? And as I mentioned before, so entanglement entropy they use, and they said it sheds light on the information propagation. So that's synonymous for what's going on here, or the ability to understand this propagation in dual artificial networks. And it said it is able to keep the same accuracy, this 90%. It was in this movie data set, and then placing minimal model in the list of, but with basically with more explainability now. So that's the 90% here with a test accuracy that you can see 90 going across. Now, this is a controllability study that I did. Now, when they say a lot of these papers, like the recent ones, it's just inherent that they're more explainable, or it's just they're inherent that they're more controllable, I saw this firsthand, and this is actually a Google demo. It's based on Tensor Network, all one word, and it works very well. It's based on TensorFlow, and what we see here is on the left, 6.4 megabyte, 1.6 million trainable parameters on the left, and on the right, 25,000 trainable parameters. And in this case, I just used 2 more additional tensor networks than the demo, and I modified the matrix size too to get it down to 96 kilobytes. So that's 65 times smaller for much better performance here. The one on the left, basically the darker blue, the better, and the brighter the yellow, the better. The dots don't move, okay? And similar run times, this one on the right was actually faster, but it's like 12 seconds compared to 9. So this was 9. And then 100%, 100 times lower loss for this one. So I wanted to take this a lot further. And in this case with parameters, so if you want to do controllability studies, you can look at changing parameters. You can change the hyperparameters, or you could change the inputs. And I did all 3 of those. So for parameters, there's these, I changed the number of hybrid layers. I changed the number of neurons. So if you get into a model that has like, this had 1,024 neurons. Now to do it on the tensor networks, I also have to change the matrix of the tensor network to match up with the end neurons, because it still has neural network on the ends, but it's not, it's basically the middle layers, these tensor networks. Then hyperparameters, I changed the learning rates, weight decays, batch sizes, and epochs, and inputs, 12 different data set size. So in all, 98 different experiments with this. And I chose these metrics of average loss, standard deviation loss, minimum loss, average time, standard deviation time, and it won 23 of the 30 categories. The main reason why this won on the right, and by the way, epoch to epoch, it was much better. So like the one on the left, a lot of times it goes 10 to the negative whatever, and then it'll go up and down in order of magnitude. But this one on the right, typically across the studies would go, just progressively lower loss, which is preferred. But basically, of these categories that it didn't win is because I was maxed out by the number of tensor network layers, and I could use 3 max, and 4 was okay, and then 5 it was just 0. So that was the main limitation of the study, is that for most of the studies it was better, but in specific cases, like I said, with the number of tensor network layers, that was an issue. And then, so here's another multiverse paper. So this was done, I think it was last year. I think they updated it in January, and actually started to hit the news again this week. And so what's shown here is basically with the MPS, or matrix product state, is it starts to get down to the performance, or the false positive rate, in this case of the autoencoder. So you see the ones above are variational autoencoder, isolation forest, and then one class SVM. And the huge thing with this is the explainability, because that's why they're pulling this paper back up, or it was Quantum Computing Report pulled this paper back up this week. And basically, it has to do with explainability, that it talked a lot about, this specific method being used with the MPS is able to do explainable AI. So you see, explainable AI cultivates trust and supports robust decision-making by providing clear explanations for outcomes, and and also with compliance with increasingly stringent transparency regulations in some industries. I think you actually face that now. So this was mostly on cybersecurity, and obviously they've done, the big paper I'll get up to, this was a leading one up to, the big llama 7 billion parameter, which I'll focus on in a little bit here too. So they say MPS, basically can be scaled easily to data sets with a huge number of features, or is remarkably memory efficient, and then on top of being accurate and explainable, as shown above. Okay, so if you see the trend now is usually they can get the author's intent is to get to that performance that was before, but now it's a lot more explainable than it was. And that's a good example of what's going on here. Now, this is Terra Quantum. And, so basically what they did is these, on the left is the tensorized network. So the embedding layer, the attention layer, and the feed forward network that I showed you kind of earlier on as part of like transformers, they compressed it using this explainable Kronecker decompositions. So still to this day, if you see tensor networks, it's still a very big thing to be compressing models to a fraction of the size, a fraction of the parameters. And like I said, I think especially for medical, is you're going to start to see this as being more and more of a, it's a priority. So it's going to be hard, at least initially, to keep that performance that, say, the top neural networks have. But in some cases, like you saw my loss study, and some cases you're able to get to better, performance as well, in addition to keeping this explainability. So they said 81 million parameters compared to 124. They did this on the GPT-2 small. And this, I don't believe this is on the market anymore, but this model's up, this GPT-2 small, and they put this, their compressed model, it's up on, I think it's PyTorch. So if you look at the paper, TQ compressor, This is getting big when the names are coming out. So we have the compact if AI here. So extreme compression of LLMs. And it's the same type of thing. We see the self-attention layer, multi-layer perceptron. Each of these red and beige highlighted ones in specific were tensorized with matrix product operators, which is the same one that I use as part of that Google demo as well. And this model, 7 billion parameters down to 30% of its size, keeping 90% of the accuracy. So I think, it just depends on the application as far as like, the exact utility you need in proving explainability in all these things. But a lot of these are lightweight operations, like a matrix product operator is typically lightweight. And that's what keeps it, efficient, fast, those types of things. And they say it actually, opens up the door for the deployment on premises of LLMs for entire new world of applications, right? So I have seen competing papers that are more traditional, i.e. they're not tensor network based or quantum inspired based. So I'm not fully convinced on that argument as far as just the size. But I think the explainability is definitely going to be there. And it seems like compared to other machine learning techniques that aren't state of the art, but are explainable, that's kind of where it has the lead. So in summary, so I showed you this before, these two different kind of interpretability, efficiency, and a lot of times I think they kind of go together. These foundations models that I mentioned before from Google Cloud as a basis for building more task-specific models, they do need an interpretability. And I think it's kind of like the wave of the future, right? Because I don't see things getting smaller as far as image analysis studies being smaller, or, we're just going to have higher parameters. But in this case, we need to have it so it's more interpretable. And same thing for medical, millions of EHRs, interacting with, this dynamic between human and AI interactions. Now, and this is what I'm getting to here in 2. So the best tensor network medical models will need a balance, right? So you need a balance between explainability, size, and performance. And obviously size is typically related to number of parameters. And the detailed explainable AI experiments, you can use SHAP, which is based on cooperative game theory, which is kind of like a standard. And LIME, I haven't heard quite as much, but that's input data perturbation. And the argument that OpenAI was saying is, why not just question all these current models 10,000 times and then analyze the accuracy of the outputs? And I think that's a valid approach too, but I think it probably will have to go a little bit further than that. As far as like with tensor networks, explainability, I don't think it's gonna, work where, it's just, all about just getting the final answer and running it a bunch of times. So in summary, tensor network approaches, they have addressed explainability, size, and performance in studies. And the ones that exist in machine learning, Bayesian networks, Boltzmann machines, they typically they don't have that higher performance that the tensor networks can get up to, as reported here. And, this year and last year, and there's one paper I was kind of like thinking to include, it's this, it's a hybrid, neural network, tensor network. It was done by NSF, funded Harvard, MIT researchers. So they found a way for it to functionally work as like a really good hybrid model, less on the compression side, but more on the functionality, the combined functionality between like a matrix product state and then the neural network. And that's in previous studies as well. And, tensor networks are also associated with high dimensional data sets, problem complexity, lower model size, less parameters, better performance, less RAM, and less time too. And I think the thing that's really, and you could see in previous weeks, I've featured TenPy, so it's tensor network like Python based, and then especially the Julia based iTensor. That seems to be in specific, like they're really starting to figure this out. They've mostly focused on kind of like the previous quantum advantage experiments and disproving those, which they've done. And now it's time to kind of like okay, we've proven that, but now it's time to like combine the best of these worlds with explainability, size, and performance as very competitive models compared to today's, llamas or GPTs or modified. They're probably modified versions of those because you can modify those in many cases. Okay. Any questions at this point? So I see there's one in the chat. So what is the main reason of compressing LLMs? It's mostly for storage size, for speed, those types of things. Ultimately, the application is in reducing it to the size of phones. So you'll hear that kind of mentioned in the news or even in just mainstream kind of tech news is you could do a lot of this, locally on your phone. And to make an analogy of it, you would still be, I believe you'd be training on your own data that you'd be collecting as you use your phone. And, that would be considered a safe way of using a compressed LLM like on your phone. Are there any other questions? And feel free to put in the chat and I can scroll back if there's a specific slide that you're looking for. Now, I did want to mention this quote here. So it's a Steve Jobs quote from Apple. So it says, you can't just ask customers what they want and then try to give that to them. By the time you get it built, they'll want something new. And that's what I've been alluding to, is we can't just have explainability. We have to be, actively pursuing high performance models that, also act like, traditional neural networks do. But now they're just a lot more explainable. So, people are always going to want high performance, but it's just like that. If you were to poll people and ask them what they want as far as like the next LLM, they want 100% explainability, 100% accuracy, 100% loss, those types of things. And then, yeah, I think it's a very well established field to the point where you can always go back to these primary kind of like machine learning TensorFlow or Tensor Network papers and pull all this up and say like, okay, this can be addressed as well. Yeah, so efficiency, typically you could do all different types of efficiency. It could be, price efficiency, but like in compute terms, it's like a loss efficiency or like a RAM efficiency. I think it's typically most often referred to as RAM, because that's an issue with high dimensional data sets. Is if you're at these high dimensions and you try to correlate all this data together, it becomes very challenging on the RAM side of things and time too. And that's what tensor networks do, is they approximate things into a more tangible tensor network. And then any other questions regarding the slides? So like, again, I expect to see a lot of, and I continue to see, these Google alerts that pop up. If you just, anytime you search for tensor networks, you still want to put it into quotes because you could still get tensors and neural networks. And if you're just trying to find tensor networks, it helps to just, put that into quotes basically. And then anybody that just came, feel free to put in the chat so you can ask other questions. And like I said, I think this is a very important field to study, because if you look for generative AI, if you look for LLMs, this is the research that everybody's super excited about. If you go to machine learning groups and they talk about these different models that have come out, that's where this is focusing, is to improve all that. Any other questions? So I do see so if you have questions, go ahead. So
yeah. I'm sorry for joining late. I was running for another meeting, but just to give some context, I'm Ala Yusuf. I'm a machine learning researcher at Stanford, focusing on LLMs in healthcare. And I think the components of AI and explainability has always been a major issue with the general models of AI, but then with LLMs, like people have been having more trust because of how it is able to mimic human behavior. And yes, you need more explanations, but it has been, what I have been observing is people are more likely to trust generative AI than traditional AI models. And I wonder where's the concept of explainability. And of course, explainability is going to be important to validate the safety and effectiveness of these large language models. But I see a shift in perception, and I wonder if that is true to other domains, or if others have thoughts on that.
Yeah, I don't know if it's like I kind of mentioned at the end is what they'll take 10,000 experiments, just run them all separately, and then evaluate the outputs or what the answers are. So to me, it sounds like generative AI might be a little bit more detailed. And I don't know if, are you comparing this to maybe like a large language model that's supervised learning, that in this unsupervised way, like is that where
Yeah,
the
I
trust?
mean, for example, to give a concrete example, initially, like most of the algorithms in medicine were, algorithm helping with image detection or report generation or something like that. It would be trained for specific tasks. And so when you give an algorithm to a clinician, they will ask you, okay, so how did the model come into this aspect of the prediction? With generative AI, because of how compelling the responses of AI, and how its ability to provide bigger context and justify, and we know the concept of hallucination confabulation, people have been asking less questions on whether, like, really, how did the LLM come into to make that report or to explain that diagnosis.
Yeah, I mean, it could be just that. There are hallucinations too. I didn't, cover today. There's 4 different reasons, and they're kind of outside this. It's more like the quality of the data going in, and 3 other reasons too. So yeah, it could be just the familiarity with generative AI, and people just tend to trust the answers. And like, say for instance, if it gives you something, you could just ask a question and it can clarify it. Um, I can't go much further than that, because everything else to me seems like a technical detail, as far as like, if this is linear in this point instead of nonlinear, then this is a more explainable approach, for this specific. And, to get to that level of like chat values and line values, it seems like, that was my understanding, is that you would have to address it like on that technical level per layer with
Yeah.
tensor networks.
Yeah.
Yeah, but I appreciate that, because that could very well be a thing, because you see it in the headlines. It's as opposed to, if you go to hospital, they're still using paper charts, that might raise some eyebrows now. Like, why don't you use medical charts? And it could be like with generative AI, that it's just such a common thing that people use all the time, that it's trusted. So yeah, I mean, I appreciate that, because I haven't heard that before.
I mean, it's just, like, of course, like, explainability and transparency and trustworthiness is something that is important to all clinicians and in the healthcare, but it has just been a shift in terms of like how initially when you give something to a clinician and they would be asking you, okay, so explain to me how the AI made that, came to that kind of like causal reasoning of how it arrived to that prediction. But now, like with the accessibility of integrating large language models within in-basket messaging, within chart workflows, within many things, things have been very smooth, and people are less likely to question or tell you, how did the large language models integrated into the Epic, for example, come to kind of like, identify that the patient needs an X-ray, for example. Um, these are type of things because of how much people have built trust, or like are quickly to trust generative AI compared to the like the simple or original traditional AI tools. But I'm sorry, this might be out of the scope, but I think concept of explainability is kind of like huge in healthcare.
Yeah, definitely. That's definitely a different perspective from what I'm used to. Bren, did you have something?
Yeah, absolutely. Yeah, thanks. First of all, I think the problem with large language models is they're very convincing. You could say they pass a Turing test. So if you talk to ChatGPT, I mean, you have the impression psychologically you're talking to a human being. Obviously, you don't. And that causes it's a psychological issue that you're more likely to trust it because it sounds like a human being, i.e. the famous Turing test. But obviously we know, as Kevin already pointed out, they hallucinate. I mean, on one occasion, I was asking for a research paper, and they actually made up the research paper with the authors and everything. So you have to be very critical. And I think they're useful as long as you cross-check the information. And the other thing we have, and that's where it gets really interesting, in the traditional neural networks, there are quite a few articles. The way they see an image is totally different from the way we see an image. So if you have a cut, we see it as a cut for a variety of reasons, the shade, the colors, but this is not how a neural network would see the cat. And I think that can make it quite difficult then to have that, to interpret it, to ask the neural network, okay, why is that a cat? Why is it a so-and-so diagnosis? Because it may see something you can't see. It may find it and it may be difficult to explain this as well, yet it might still be valid. So I think we have a bit of a conundrum that that neural networks can extract information, or I think any kind of AI, that is not necessarily explainable easily for us, and it will be quite a challenge to sort of and I think lots of work is going into this to probe the individual layers to find out how does the network arrive at that information. Because for the clinician coming back, it's important that we can explain what we're doing. There's an audit trail. So if we think it's cancer, we have to have a good enough reason to think it's cancer. But the challenge is if the AI tells us it is cancer, but it can't explain why it is, what do we do then? That's the conundrum. Thank you.
Yeah, that's a really good, exactly the conundrum we are in, right? And like we have been struggling in. And I think, like to that point, the point I feel like, as a cognitive scientist, an ML researcher, I feel like the point is people are thinking AI needs to be explainable in the way human think, and we know an AI is more complex than that, and the way it interprets and learns from pattern and data is similar but quite distinct from humans. And so like there's that general of you need to kind of like educate people about what is really explainable AI, but I think like there's also a need for more broader understanding of what are tools to make large language model explainable, and how reliably can we trust these approaches, and what is the future of it. I feel like that this is really currently like an area where we need to have a better understanding of it, because as these models get very good in terms of articulating, as Brandon, you mentioned, we need to be able to cross-reference and really be able to check the validity of the outputs of these generative AI.
Yeah, absolutely. Yeah. And I think obviously there's a big push for new applications. And like now we can go from like text straight into getting an image or a video. I was part of some other kind of coding groups, and they said that it's not too far that you could just type in and it could produce like a top 10 radio hit, like in the Billboard today, that type of stuff. So you're going to get that where performance is pushing one way, but it might be pushing against explainability. But I think for fields that really need to find out how exactly the AI got to that solution, that there'll start to be a push for that and a big market for it.
Yeah, sounds great. Thank you so much.
Yeah, you're welcome. Anybody we haven't heard from? Yeah, it's definitely an exciting field. If you go to a lot of the other machine learning meetups, it's typically just accuracy loss, those types of things. I haven't heard it. I go to like an advanced machine learning group the past several months, and explainability doesn't come up nearly as much. And asking about SHAP values, that might have been the first time it got brought up, just because there's many other areas that just want like the utility, the application of it, as opposed to saying like how trustworthy is it, even as we start to trust, Gen AI more.
Yeah, Kevin, one more question. What are your thoughts on scalability? I mean, in a way, tensor networks are sort of an attempt to use classical computing to simulate quantum, but the problem you always run into at some point is the exponential scale up. There simply is a limit for classical computing, whether it's tensor or anything else. How far do you think we can scale up classical before we run into this sort of exponential wall.
Yeah, so the best example of this is the iTensor. So it's Flatiron Institute that runs iTensor. So under that is like iTensor Networks, and it's mostly Julia or C++. And they just had a big paper out this year. And what it is they took 127 qubit. It's called a kicked icing model on IBM Eagle quantum processor. So they went over to replicate exactly how it was done on the quantum computer, and it ran so much faster, more precise, more accuracy. And on top of that, they said it's scaling mathematically to what corresponds to an infinite number of qubits. So meaning that running all of this tensor networks, if you want to do, quantum algorithms like you would on a quantum computer, now you're not mathematically bounded to like an exponential RAM, or going exponential in time. And they used a specific technique called belief propagation, BP. So they used that, and they said, it's looking pretty good as far as whatever we want to do, we can do on tensor networks that you would do on quantum hardware. And it's 10 times more, or it's like infinitely more practical, readily available, cost effective, those types of things.
I mean, the main advantage I see, it's a logical qubit as opposed to a noisy qubit. But I'm not quite sure about this infinite scale up. I think that's just sort of mathematical modeling. So I would be a bit skeptic about this because lots of companies have come up with bold claims. Google was one example. It does make headlines, but I'm not entirely sold on it.
Yeah, I mean, if you want to take it a step further, there was another paper by IonQ and IBM. You probably saw this paper, and there was a neutral atom experiment late last year, like 48 qubits, and they did it on classical hardware much faster, like 100 times faster, no error correction needed. They scaled it up double to 96, and then they scaled it up again to 192 qubits, and that's where it really took some more hardware, like what it would be for like deep learning of like with 4 days of deep learning. So yeah, we're getting to even that was state vector simulation, which it's an exact approximation, but the tensor network stuff is controlled approximation. So it's, it's doing things in approximate manners. So you can get to these infinite numbers of qubits, and it's mathematically possible.
Yeah, I pass on this. I'm not entirely convinced. I mean, usually it's problem specific. It probably depends on the kind of problem they're trying to solve.
Yeah, there are some restrictions with tensor networks. So highly entangled systems, it's just too much math involved with that. So there are some things, but it's not nearly what you face if you're trying to run on quantum hardware with noise and decoherence and, algorithm issues, and the list goes on and on. So
yeah, I think that's the issue. It's a logical qubit, and you would need many actual qubits.
Yeah. So, and I would take a look at it, Beren. So I put it on my LinkedIn. So it's 18 different reasons why quantum computers won't be used for AI at all. And the main reason is that the pace of AI is moving so fast that it can't wait around for something that it just has to work, and it has to be improving it like tensor networks are today. So in 5 years, they say like, hardly any people will be coding, and Gen AI is going to be doing a lot of these tasks for us. Is that will not just sit and wait for other technologies. It has to be ready today. And, classical CPUs, GPUs, or TPUs too. So yeah, it's the pace of AI. I mean, if you want to talk about other technologies, that might be in a consideration. There's other issues involved with that, but for AI, it won't slow down to be.
Oh no, absolutely not, because it's a race basically, and the funny thing is that classical seem to win out, but the quantum development has also spurred on classical development. That's the interesting part. And you're using similar techniques. You demonstrated it today. Mathematical techniques that work for quantum can also be applied to classical computing. And on the 1st of April, Zapata Computing, you have heard about them, will list on the Nasdaq and they're a company that's exploring exactly this sort of field of classical computing, but using quantum-inspired algorithms.
Yeah, and I'm more or less it's the technology that's required to implement into today's AI. Because if it just has to, take all of this time just to incorporate and it doesn't improve AI today, then in 5 years, I don't see those technologies being a factor, anything that can't run today and improve AI today. I don't see any other technology really, being in that argument just because it takes so much and the current tech is going to advance so fast too. So like I said, for other technologies, maybe, but yeah, the pace of AI. So one of my colleagues in a different meetup, he said that by the time you go to deploy a model and click play, it's already out of date, for an AI model, because that's how fast that they're released. And there's just so much development for, LLMs. And
that's absolutely true.
Yeah. So for generative AI and these types of things.
Good stuff. Yeah. Thank you.
Yeah. So any other questions? Anybody that we haven't heard from? So Mo or Anand?
No, I don't have any questions. But I wanted to say thanks for the presentation. I learned a lot. And yeah, the explanatory of the machine learning models are a big thing, but I don't know how necessary they are. So
Okay. Yeah, I'm learning too, because like I said, I'll watch a bunch of seminars and read papers, and it's just good to get all of this feedback too. I think it's very necessary. So I was just watching a Stanford Medicine. They just did a big AI kind of panel earlier this week, and they had specifically brought up the explainability of models as being an issue, driving into the future. And so that caught my attention. And the open AI that I included at the end of this, it was Sam Altman up on a stage recently, and he did say, explainability is an issue. They want to get it better. And, I think ultimately, if you're generating, like your favorite, pets or animals eating dinner at a table, and now you needed that performance to get to that specific application of that perfect image that might not require the explainability, but I kind of see tensor networks, just gradually being involved in the system. And now we're talking about very significant portions being tensorized, like they have in the past, but just to a greater degree, And I think the thing that people don't understand is that there is quantum physics or quantum mechanical nature behind it. So they might not know how to use that right away. And the software libraries like iTensor and TenPy, I think iTensor is like right on spot right now, but it's just, maybe a little bit more demos, just basic models or recognition models or classification or something like a BERT or something like that, that's been done with a tensor network. Then you can kind of play around with that. TenPy, which is Python based, that just hit 1.0, which is a good sign. And the iTensor, they just went to like 40 papers this year so far, and then TenPy is at about 19. And my understanding is with the iTensor, you can take it very far, especially like belief propagation from that one paper. But I would definitely check into iTensor, and they have a good discourse. And the GitHub they have many subdirectories with that too.
yeah, makes sense. But I mean, the way that I look at the explainability of the model is like, well, I mean, human beings are almost the same. They're a black box where you teach them something, like, for instance, in this case, like medicine. I mean, you don't really try to explain like how did they learn it. You just sort of give some exams and test them, and if they pass, you just
but let's take an example. Let's look like an MRI image. You're looking for cancer. If you're a radiologist, you have certain criteria, a list of criteria you go through. You know what the normal tissue looks like, and then you see a lesion and doesn't look quite right. But if the AI can't give you that information, let's say the AI is flagging up that this could be cancer, but can't give you an explanation, then you have a problem as a clinician. because you have to make a decision. The person could have surgery or radiotherapy. If you get this wrong, if someone who doesn't have cancer gets treatment, then you're in a very difficult position and vice versa. So you have to be able to explain while you make this decision. It's what we call an audit track. And that's really important in a clinical environment. So if the system just tells you there's cancer, that won't really be sufficient in many cases to make a decision. And I mean, this could go to a court. There could be a legal case. Things go wrong. How do you defend yourself? That's a big question.
Yeah, and I thought that you earlier brought up a really good point as far as layer by layer, going through from here to here. Now, there are a lot of convolutional neural networks that are FDA approved, and I think that it would benefit from having more explainability. A lot of times you can't replace all of so say like on the terminal ends, you're still going to have some dense layers, but then some tensor networks in between, and then you could arrive at a better interpretability.
Yeah, I think the exception would be if you have, let's say, a network, if you have an AI that can make really, really good high-level predictions where you know that it's a ridiculous sensitivity of 99.9%. And even if you then didn't know why it is, but if you can demonstrate that all your research always came up with a really high sensitivity and specificity, I think that might be something where even if you can't fully explain it, it might be usable, but you would have to have really accurate predictions. But most predictions aren't actually that accurate, whether they're human or not, whether they're human or machine. That's the problem, I think.
Yeah, definitely. And what was I thinking? So the other thing is probable benefit over probable risk, because if you look at these, because there's already a lot of approved algorithms out there that they just they don't have high degrees of explainability. And I think the main thing is they're run a ton of times in different ways, and you can update the algorithms if you need to. But it's the type of thing like it would give additional kind of like peeking into how the answers are gotten if certain layers aren't as nonlinear.
Yeah, or the other example would be there's another test. So the AI tells you there's a problem, and then you can do a clinical test that gives you a yes or no answer. That would be another example where you don't need explainability because you have another test you can rely on. So I think it depends on the context as well.
Yeah, I appreciate the discussion for sure. Anybody else? Or Mo, did you have something?
No, I just wanted to say that, yeah, that's right. I kind of see that. I mean, legal problems are a big big push to this problem for sure. And like in the future, maybe if we like how we trust human beings, if we trust the machine learning models and change the rules to sort of back up those decisions, maybe we have less problems to need to try to explain those models.
Yeah, and I think the further this goes, as far as like compute power, and especially in radiomics, as far as like trying to train every single medical image that we've seen, if it's relevant, I don't think that's a fully established field yet, but that would be something that could potentially be beneficial if it was more explainable as far as how the computer got to the solutions.
Right. Yes.
Yeah. So yeah, very cool. And anybody else we haven't heard from, or definitely keep posted. Like I said, I put a Google alert for Tensor Networks for sure, and quote in the tensor and the networks because it's not good at distinguishing that on its own yet. But yeah, there's a lot of good literature. Those papers I'll have up, and then you can go through some of those reviews as well. Awesome. Any other last comments or questions? Appreciate everybody coming from different parts of the world. And then if not, this has been event seminar 128, Thursday, March 28th, 2024 for LLM explainability and controllability with Tensor Networks. Appreciate everybody coming on. Have a good rest of the night and have a productive rest of the week, everybody. Take care.
Bye. Take care.